Chapter 3: Storage and Retrieval. On the most fundamental level, a database needs to do two things. When you give some data, it should store the data. When you ask it again later, it should give you the data back to you. In Chapter 2, we discuss data models and query languages. Example the format in which you, the application developer, give the database your data and the mechanism by which you can ask for it again later. In this chapter, we discuss the same from the database point of view, how we can store the data that we are given and how we can find it again when we are asked for it. Why should you, as an application developer, care how the database handles storage and retrieval internally? You are probably not going to implement your own storage engine from scratch, but you do need to select the storage engine that is appropriate for your application from the many that are available. In order to tune a storage engine to perform well on your kind of workloads, you need to have a rough idea of what the storage engine is doing under the hood. In particular, there's a big difference between storage engines that are optimized for transactional workloads and those that are optimized for analytics. We will explore that distinction later in transaction processing or analytics on page 90 and in columns-oriented storage on page 95. We will discuss a family of storage engine that is optimized for analytics. However, first we will start this chapter by talking about storage engines that are used in these kind of databases that you're probably familiar with. Traditional relational databases and also also called NoSQL databases. We'll examine two families of storage engine: log structure storage engines and page-oriented storage engines, such as B-trees. Data structures that power your database. Consider the world's simplest database implemented as two batch functions. These two functions implement a key value store. You can call dbSet key value, which will store key and value in the database. The key and value can be almost anything you like. For example, the value could be a JSON document. You can then call dbGet key, which looks up the most recent value associated with the particular key and returns it. And it works. The underlying storage format is very simple. A text file where each line contains a key value pair separated by commas, roughly like a CSV file, ignoring escaping issues. Every call to dbSet appends to the end of the file. So if you update a key several times, the older version of the value are not overwritten. You need to look at the last occurrence of the key in the file to find the latest value, hence the tail and 1 in dbGet. Our dbSet function actually has pretty good performance for something that is so simple, because appending to a file is generally very efficient. Similarly to what dbSet does, many databases internally use a log, which is an append-only data file. Real databases have more issues to deal with, such as concurrency control, reclaiming this space so that the log doesn't grow forever, and handling errors and particular written records. But the basic principle is the same. Logs are incredibly useful, and we will encounter them several times in the rest of this book. The word logs is often used to refer to the application logs, where an application output text that describe what happens in this book. Log is used in the more general sense, an append-only sequence of record. It doesn't have to be human readable. It might be binary and instead only for other programs to read. On the other hand, our dbGet function has better performance if you have a large number of records in your database. Every time you want to look up a key, dbGet has to scan the entire database file from the beginning to the end, looking for occurrences of the key. In algorithmic terms, the cost of the lookup is O the n. If you double the number of records n in your database, a lookup takes twice as long. That's not good. In order to efficiently find the value for a particular key in the database, we need a different data structure, an index. In this chapter, we will look at the range of indexing structure and see how they compare. The general idea behind them is to keep some additional metadata on the side, which act as a signpost and it helps you to locate the data you want. If you want to search the same data in several different ways, you may need several different indexes on different part of the data. An index is an additional structure that is derived from the primary data. Many databases allow you to add and remove indexes, and this doesn't affect the content of the databases. It only affects the performance of queries. Maintaining additional structures incur overhead, especially on writes. For writes, it's hard to beat the performance of simply appending to a file, because that's the simplest possible write operation. Any kind of index usually slow down writes, because the index also needs to be updated every time data is written. This is an important trade-off in storage systems. Well, chosen indexes speed up read queries, but every index slows down writes. For this reason, databases don't usually index everything by default, but require you, the application developer or database administrator, to choose indexes manually. Using your knowledge of the application typical query patterns, you can then choose the index that gives your application the greatest benefit without introducing more overhead than necessary. Hash indexes. Let's start with indexes for key value data. This is not the only kind of data you can index, but it's very common and is useful building block for more complex indexes. Key value stores are quite similar to the dictionary type that you can find in most programming languages, and which is usually implemented as a hash map, hash table. Hash map are described in many algorithms textbooks, so we won't go into detail of how they work here. Since we already have a hash map for our in-memory data structure, why not use them to index our data on disk? Let's say our data storage consists only of appending to a file, as in the preceding example. Then the simplest possible indexing strategy is this. Keep an in-memory hash map where every key is mapped to a byte offset in the data file. The location at which the value can be found, as illustrated in figure 3.1, whenever you append a new key value paired to the file. You also update the hash map to reflect the offset of the data you just wrote. This works both for inserting new keys and for updating existing keys. When you want to look up a value, use the hash map to find the offset in the data file. Seek to the tool to that location and read the value. This may sound simplistic, but it is a viable approach. In fact, it is essential what Bitcask, the default storage engine in React, does. Bitcask offers high-performance reads and writes, subject to the requirement that all the keys fit in the available RAM, since the hash map is kept completely in memory. The value can use more space than there is available memory, since they can be loaded from disk with just one disk. Sick. If that part of the data file is already in the file system cache, a read doesn't require any disk I/O at all. A storage engine like Bitcask is well suited to situations where the value for each key is updated frequently. For example, the key might be the URL of a cat video, and the value might be the number of times it has been played, incremented every time someone hits the play button. In this kind of workload, there are a lot of writes, but there are not too many distant keys. You have a large number of writes per key, but it's feasible to keep all keys in memories. As described so far, we only ever append to a file, so how do we avoid eventually running out of this space? A good solution is to break the log into segments for a certain size by closing a segment file when it reaches a certain size and making subsequent writes to a new segment file. We can then perform compaction on this segment, as illustrated in figure 3.2. Compaction means throwing away duplicated keys in the log and keeping only the most recent update for each key. Moreover, since compaction often makes segments much smaller, assuming that a key is overwritten several times on average, within one segment, we can also merge several segments together at the same time as performing the compaction. As shown in figure 3.3, segments are never modified after they have been written, so the merged segment is written to a new file. The merging and compaction of frozen segments can be done in a background thread, and while it is going on, we can still continue to serve reads and write requests as normal, using the old segment file. After the merging process is complete, we switch reads requests to using the new merged segmented instead of the old segment, and then the old segment files can simply be deleted. Each segment now has its own in-memory hash table, mapping keys to file offset. In order to find the value for a key, we first check the most recent segment hash map. If the key is not present, we check the second most recent segment and so on. The merging process keeps the number of segments small, so lookups don't need to check many hash maps. A lot of detail goes into making this simple idea work in practice. Briefly, some of the issues that are important in real implementation are: file format. CSV is not the best format for a log. Faster and simpler to use a binary format that first encodes the length of the string in bytes, followed by a raw string without need for escaping. Deleting records. If you want to delete a key and its associated value, you have to append a special deletion record to the data file, sometimes called tombstone. When log segments are merged, tombstones tell the merging process to discard any previous value for the deleted key. Crash recovery. If the database is restarted, the in-memory hash maps are lost. In principle, you can restore each segment's hash map by reading the entire segment file from beginning to end and noting the offset of the most recent value for every key as you go along. However, that might take a long time if the segment files are large, which would make serves restart painful. It cuts speed of recovery by storing a snapshot of each segment hash map on disk, which can be loaded into memory more quickly. Partially reading records. The database may crash at any time, including halfway through appending a record to the log, be it cache files include checksums, allowing such corrupted part of the log to be detected and ignored. Concurrency control. As writes are appended to the log in a strictly sequential order, a common implementation choice is to have only one reader thread. Data file segments are append only and otherwise immutable. So they can be read concurrently by multiple threads. An append only log seems wasteful at first glance. Why don't you update the file in place, overwriting the old value with the new value? But an append only design turns out to be good for several reasons. Appending and segments merging are sequential write operations, which are generally much faster than random writes, especially on magnetic spinning disk hard drives. So, to some extent, sequential writes are also preferable on flash-based solid-state drives. We will discuss this issue further in comparing B trees and LSM trees on page 83. Concurrency and crash recovery are much simpler. If segment files are append only or immutable, for example, you don't have to worry about the case where a crash happened while the value was being overwritten, leaving you with the file containing part of the old and part of the new value spliced together. Merging all segments avoid the problem of data files getting fragmented over time. However, the hash table index also has limitations. The hash table must fit in memory. So if you have a very large number of keys, you are out of luck. In principle, you could maintain a hash map on disk, but unfortunately, it is difficult to make and on this hash map perform well. It requires a lot of random access I/O. It's expensive to grow when it becomes full, and hash collision required fiddly logic. Range queries are not efficient. For example, you cannot easily scan over all keys between kitty 00000 and kitty 99999. You have to look up each key individually and in the hash map. In the next section, we will look at the index structures that doesn't have those limitations. SS tables and LSM trees. In figure 3.3, each log structure storage segment is a sequence of key values pairs. These pairs appear in the order that they were written, and values later in the log take precedence over value for the same key early in the log. Apart from that, the order of key value pairs in the file doesn't matter. Now we can make a simple change to the format to our segment files. We require that the sequence of key value pair is sorted by key. At first glance, that requirement seems to break our ability to use sequential writes, but we get to that in a moment. We call this format sorted string tables, SSL tables for short. We also require that each key only appears once within each merged segment file. The compaction process already ensures that. SSL tables have several big advantages over log segments, which had index. 1. Merging segments is simple and efficient, even if the files are bigger than the available memory. The approach is like the one used in the merge sort algorithm, and is illustrated in figure 3.4. You start reading the input files side by side. Look at the first key in each file. Copy the lowest key according to the sort order to the output file and repeat. This produces a new merge segment file also sorted by key. What if the same key appears in the several input segments? Remember that each segment contains all the values written in the database during some period of time. This means that all the values in one input segment must be more recent than all the values in other segments, assuming that we always merge adjacent segments. When multiple segments contain the same key, we can keep the value from the most recent segment and discard the value in other segments. 2. In order to find a particular key in the file, you no longer need to keep an index of all the key memories. See figure 3.5 for example. Say you are looking for the key handiwork, but you don't know where the exact offset of that key in the segment file. However, you do know the offset for the key handbag and handsome, and because of the sorting you know that handiwork must appear between these two. This means you can jump to the offset for handbag and scan from there until you find handiwork or not, if the key is not present in the file. You still need an in-memory index to tell you the offset for some of the keys, but it can be sparse. One key for every few kilobytes of segment file is sufficient, because a few kilobytes can be scanned very quickly. Since reads requests need to scan over several key value pairs in the request range anyway, it is possible to group those records into a block and compress it before writing into a disk, indicated by the shaded area in figure 3.5. Each entry of the sparse in memory before writing to a disk, indicated the shaded area in figure 3.5. Each entry of the sparse in memory index then points at the start of the compressed block. Besides saving this space, compression also reduces the I/O bandwidth use. Constructing and maintaining SSL stable. Fine so far, but how do we get your data to be sorted by key in the first place? Our incoming writes can occur in any order. Maintaining a sort structure on this is possible. See B3 on page 79. But maintaining it in a memory is much easier. There are plenty of well-known tree data structures that you can use, such as red-black trees or ABL trees. With these data structures, you can insert keys in any order and read them back in sorted order. We can now make our storage engine work as follows. When a write comes in, add it to the in-memory balance tree data structure. For example, a red-back delete. This in-memory tree is something called mem table. When the mem table gets bigger than some threshold, typically a few megabytes, we'll write it out to a disk to access a table file. This can be done efficiently because the tree already maintains the key value pair sorted by key. The new SSL table file becomes the most recent segment of the database, while the SSL table is being written out to the disk. Writes can continue to a new memtable instance. In order to serve a read request, first try to find the key in the memtable, then in the most recent on this segment, then in the next older segment, etc. From time to time, run a merging and compaction process in the background to combine segment files and to discard overwritten or deleted values. This schema works very well. It's only suffered from one problem. If the database crashes, the most recent writes, which are in the mem table but not yet written out of this, are lost. In order to avoid that problem, we can keep a separate log on this to which every write is immediately appended, just like in the previous section. That log is not in sorted order, but that doesn't matter because its only purpose is to restore the mem table after a crash. Every time the mem table is written out to an SSD table, the corresponding log can be discarded, making an LSM tree out of SSS table. The algorithm described here is essentially what is used in LevelDB and RockDB, key value storage engine library that are designed to be embedded into other applications. Among other things, LevelDB can be used in Riot as an alternative to Biscask. Similar storage engines are used in Cassandra and HBase, both of which were inspired by Google Big Table papers, which introduced the term SSS tables and mem tables. Originally, this index structure was described by Patrick O'Neill et al. Under the name Log Structure Merge Tree, or LSM3, building on early work on log structure file system. Storage engines that are based on this principle of merging and compacting sorted files are often called SMS storage engine. To see an index engine for full text search used by Elasticsearch and SOAR use a similar method for storing its term dictionary. A full text index is much more complex than a key value index, but it's based on a similar idea. Giving a word in a search query, find all the documents, web pages, product description, etc. that mention the word. This is implemented with a key value structure where the key is a word, a term, and the value is the list of IDs of all the documents that contains the word, the positive list, in Lucid. This mapping form terms to posting list is kept in SSA table like sort file, which are merged in the background as needed. Performance optimization. As always, a lot of details goes into making a storage engine perform well in practice. For example, the LSM3 algorithm can be slow when looking up keys that do not exist in the database. You have to check the mem table, then the segment all the way back to the oldest, possibly having to read from this for each one, before you can be sure that the key does not exist. In order to optimize this kind of access, storage engines often use additional Bloom filters. A Bloom filter is a memory-efficient data structure for approximating the content of a set. It can tell you if a key does not appear in the database and thus save me many unnecessary disk reads or non-existent performance optimizations. As always, a lot of detail goes into making a storage engine perform well in practice. For example, the LSM3 algorithm can be slow when looking up keys that do not exist in the database. You have to check the mem tape, then the segments all the way back to the oldest, possibly having to read from this for each one, before you can be sure that the key does not exist. In order to optimize this kind of access, storage engines often use additional Bloom filters. A Bloom filter is a memory-efficient data structure for approximating the content of a set. It can tell you if a key does not appear in the database and thus save many unnecessary disk reads for non-existent keys. There are also different strategies to determine the order and timing of how SSL tables are compacted and merged. The most common options are size, tiered, and level-led compaction. LevelDB and RockDB use level compaction, hence the name of LevelDB. HBase use size tiered, and Cassandra support both. Inside tiered compaction, newest and smallest SS tables are successively merged into older and large SSS tables. In level compaction, the key range is split up into smaller SS tables, and all the data is moved into separate levels, which allow the compaction to proceed more incrementally and use less disk space. Even though there are many subtleties, the basic idea of LSM3 keeping a cascade of SSL tables that are merged in the background is simply ineffective. Even when the data set is much bigger than the available memory, it continues to work well. Since data is stored in a sorted order, you can efficiently perform range queries, scanning all keys above some minimum and up to some maximum. And because the disks write are sequentially, the SM3 can support remarkably high reading throughput. B-trees. The log structure index we have discussed so far are gaining acceptance, but they are not the most common type of index. The most widely used index structure is quite different, the B-tree. Introduced in 1970 and called ubiquitous, less than 10 years later, B-trees have stood the test of time very well. They remain the standard index implementation in almost all relational databases, and many non-relational databases use them too. Like SSL table, B-tree keep key value pairs sorted by key, which allows efficient key value lookups and ranges queries. But that's where the similarity ends. B-trees have a very different design philosophy. The log structure index we saw earlier break the database down into variable size segments, typically several megabytes or more in size, and always write a segment sequentially. By contrast, B-tree breaks the database down into fixed size blocks or pages, traditional 4 kilobytes in size, sometimes bigger, and reads or writes one page at a time. This design corresponds more closely to the underlying hardware, as these are also arranged in fixed size blocks. Each page can be identified using an address or location, which allow one page to refer to another, similar to the pointer, but on disk instead of in memory. We can use these page references to construct the tree of page, as illustrated. One page is designated as the root of the B tree. Whenever you want to look up a key in the index, you start here. The page contains several keys and references to child pages. Each child is responsible for a continuous range of keys, and the keys between the reference indicate where the boundary between those ranges lie. In the example in figure 3.6, we are looking for the key 251, so we know that we need to follow the page reference between the boundaries 200 and 300 that take us to a similar looking page that further breaks down 200 and 300 ranges into sub-ranges. Eventually, we get down to a page containing the individual key, a leaf page, which either contains the value for each key in line or contains reference to the pages where the value can be found. The number of references to child pages in one page of B-tree is called a branching factor. For example, in figure 3.6, the branching factor is 6. In practice, the branching factor depends on the amount of space required to store the page reference and the range boundaries, but typically it is several hundred. If you want to update the value for an existing key in a B-tree, you search for the leaf page containing that key, change the value in that page, and write the page back to disk. Any reference to that page remains valid. If you want to add a new key, you need to find the page whose range encompasses the new key and add it to that page. If there is not enough free space in the page to accommodate the new key, it is split into two half-full pages. and the parent page is updated to account for the new subdivision of key ranges. These algorithms ensure that the tree remains balanced. A B tree with n key always has a depth of O log n. Most databases can fit into B trees that is 3 or 4 levels deep, so you don't need to follow many pages reference to find the page you are looking for. A 4-level tree of 4 kilobytes pages with a branching factor of 500 can store up to 256 terabytes of data, making B trees reliable. The basic underlying write operation of a B tree is to overwrite a page on disk with new data. It assumes that the overwrites do not change the location of the page. All reference to that page remain intact when the page is overwritten. This is in stark contrast to log structure indexes such as LSM3, which only appends to file and eventually delete obsolete file, but never modify files in a place. You can think of overreading a page on disk and actually hardware operation on a magnetic hard drive. This means moving the disk ahead to the right place, waiting for the right position on the spinning plate to come around, and then overreading the appropriate sector with the new data. On SSD, what happens is somewhat more complicated due to the fact that an SSD must erase and rewrite fairly large block of storage chip at a time. Moreover, some operations require several different pages to be rewritten. For example, if you split a page because an insertion caused it to overflow, you need to write the 2 pages that were split and also overwrite their parent page to update the reference to the 2 child pages. This is a dangerous operation because if the database crashes after only some of the pages have been written, you end up with a corrupt index. There may be an orphan page that is not a child of a parent. In order to make the database resilient to crashes, it is common for B-tree's implementation to include an additional data structure on disk, a write-ahead log, a WAL, also known as redo log. This is an append-only file to which every B-tree modification must be written before it can be applied to the pages of the tree itself. When the database comes back after a crash, this log is used to restore the B-tree back to a consistent state. An additional complication of data pages in place in that the careful concurrency control is required if multiple threads are going to access the B tree at the same time. Otherwise, a thread may see the tree in an inconsistent state. This is typically done by protecting the tree data structure with latches, lightweight locks. Log structure approaches are simpler in this regard because they do all the merging in the background without interfering with incoming queries and atomically swap old segments for new segments from time to time. B-trees optimizations. As B-trees have been around for so long, it's not surprising that many optimizations have been developed over the years. To mention just a few, instead of overreading pages and maintaining a WAL for crash recovery, some databases like LMDB use a copy and write scheme. A modified page is written to a different location, and a new version of the parent's pages in the tree is created pointing at the new location. This approach is also useful for concurrency control, as we shall see in snapshot isolation and repeatable read on page 237. We can save space in page by not storing the entire key, but reading is especially in pages on the interior of the tree. Keys only needs to provide enough information to act as boundaries between key ranges. Packing more keys into a page allows the tree to have a higher branching factor and thus fewer levels. In general, pages can be repositioned anywhere on disk. There is nothing required in pages with nearby key ranges to be nearby on disk. If a query needs to scan over a large part of the key ranges in sorted order, that page-by-page layout can be inefficient because a disk seek may be required for every page that is read. Many B-trees implementation therefore try to lay out the tree so that the leaf pages appear in sequence order on the disk. However, it's difficult to maintain that order as the tree grows, By contrast, since LSM3s rewrite large segments of the storage in one go during merging, it is easier for them to keep sequentially key close to each other on disk. Additional pointers have been added to the tree. For example, each leaf page may have reference to its sibling page to the left and right, which allows scanning keys in order without jumping back to parent pages. B-tree variants such as fractal trees borrow some log structure ideas to reduce disk 6, and they have nothing to do with fractals. Comparing B-trees and LSM trees. Even though B-trees implementation are generally more non-mature than LSM trees implementation, LSM trees are also interesting due to their performance characteristics. As a rule of thumb, LSM trees are typically faster for writes, whereas B-trees are thought to be faster for reads. Reads are typically slower on LSM trees because they have to check several different data structures and SSL tables at different stages of compaction. However, benchmarks are often inconclusive and sensitive to deal of the workload. You need to test system with your particular workload in order to make a valid comparison. In this section, we will briefly discuss a few things that are worth considering when measuring the performance of a store engine. Advantage of LSM trees. A B-tree index must write every piece of data at least twice. Once to the write-ahead log and once to the tree page itself. And perhaps against page are split. There is also overhead from having to write an entire page of a time, even if only a few bytes in that page change. Some storage engines even already write the same page twice in order to avoid ending up with a partially updated page in the event of a power failure. Log structure index also rewrites data multiple times due to the repeat compaction and merging of SSL table. This affects one write to the database, resulting in multiple writes to the disk over the course of the database lifetime. It's known as write amplification. It is of particular concern on SSD, which can only overwrite blocks a limited number of times before reading out. In writes-heavy application, the performance bottleneck might be the rate at which the database can write to disk. In this case, write amplification has a direct performance cost. The more than the storage engine write to disk, the fewer write per second it can handle within the available disk bandwidth. Moreover, LSM trees are typically able to sustain higher write throughputs than B trees, partly because they sometimes have lower write amplification, although this depends on the storage engine configuration and workload, and partly because they sequentially write compact SSD files rather than having to overwrite several pages in the tree. This difference is particularly important on magnetic hard drives, where sequential writes are much faster than random writes. LSM trees can be compressed better and thus often produce smaller files on disk than B trees. B-tree's storage engine leaves some disk space unused due to the fragmentation. When a page is split or when a row cannot fit into an existing page, some space in a page remains unused. Since LSM trees are not page-oriented and periodically rewrite SSL tables to remove fragmentation, they have lower storage overhead, especially when using leveled compaction. On many SSD, the firmware internally uses a log structure algorithm to turn random writes into sequential writes on the underlying store chips. So the impact of the store engine write pattern is less pronounced. However, lower write amplification and reduced fragmentation are still advantages on SSDs, representing data more compactly allows more read and write requests with the available I/O bandwidth. Downside of LSM trees. A downside of a log structure storage is that the compaction process can sometimes interfere with the performance of ongoing reads and writes. Even though storage engines try to perform compaction incrementally and without affecting concurrent access, these have limited resources, so it can easily happen that requests need to wait while the disk finishes, an expensive compaction operation. The impact on throughput and average response time is usually small, but a higher percentile. See describing performance on page 13. The responsible time of query to log structured storage engines can sometimes be quite high, and B-trees can be more predictable. Another issue with compaction arises at high write throughput. The disk's finite write bandwidth need to be shared between the initial writes. Logging and flushing a mem table to disk, and the compaction thread running in the background. When writing to an empty database, the full disk bandwidth can be used for the initial write, but the biggest dataset gets, the more disk bandwidth is required for compaction. If write throughput is high and compaction is not configured carefully, it can happen that compaction cannot keep up with the rate of incoming write. In this case, the number of unmerged segments on disk keep growing until you run out of disk space, and read also slow down because they need to check more segment files. Typically, SSS tables based storage engines do not throttle to rate of incoming writes, even if compaction cannot keep up, so you need explicit monitoring to detect this situation. An advantage of B-tree is that each key exists in exactly one place in the index, whereas a log structure storage engine may have multiple copies of the same key in different segments. These aspects make B-trees attractive in databases that want to offer strong transaction semantics. In many relational databases, transaction isolation is implemented using log on ranges of key, and in a B-tree index, those logs can be directly attached to the tree. In Chapter 7, we will discuss this point in more detail. B-trees are very ingrained in the architecture of databases and provide consistently good performance for many workloads, so it's unlikely that they will go away anytime soon. In new data stores, log structures index are becoming increasingly popular. There is no quick and easy rule for determining which type of storage engine is better for your use case, so it's worth testing empirically. Other indexing structures. So far, we have only discussed key value indexes, which are like a primary key index in the relational model. A primary key uniquely identifies one row in a relational table, or one document in a document database, or one vertex in a graph database. Other records in the database can refer to the row document vertex by its primary key or ID, and the index is used to resolve such reference. It is also very common to have a secondary index. In relational databases, you can create several secondary indexes on the same table using a create index command, and they are often crucial for performing joins efficiency. For example, in Figure 2.1 in Chapter 2, you will most likely have a secondary index on the user ID columns so that you can find the rows belonging to the same user in each of the table. A secondary index can easily be constructed from a key value index. The main difference is that keys are not unique. There might be many rows, documents, vertices with the same key. This can be solved in two ways, either by making each value in the index a list of matching rows identifiers, like a posting list in a full text index, or by making each key unique by appending a row identifier to it. Either way, both B-tree and log structure indexes can be used as secondary indexes. Storing value within the index. The key in an index is the thing that queries search for, but the value can be one of two things. It could be the actual row, document, vertex in question, or it could be a reference to the row stored elsewhere. In the latter case, the place where rows are stored is known as heap file, and it stores data in no particular order. It may be append only, or it may keep track of deleted rows in order to read them with new data later. The heap file approach is common because it avoids duplicating data when multiple secondary indexes are present. Each index just references a location in the heap file, and the actual data is kept in one place. When updating a value without changing the key, the heap file approach can be quite efficient. The record can be written in place, provided that the new value is not larger than the old value. The situation is more complicated if the new value is larger, and it probably needs to be moved to a new location in the heap where there is enough space. In that case, Either all indexes need to be updated to point out the new heap location of the record, or forwarding pointer is left behind the old heap location. In some situations, the extra hop from the index to the heap file is too much of a performance penalty for reads, so it can be desired to store for the index or directly within an index. This is known as cluster index. For example, in MySQL, InnoDB storage engine, the primary key of a table is always a cluster index, and secondary indexes refer to the primary key rather than a heap file location. In SQL Server, you can specify one cluster index per table. A compromise between a cluster index storing all rows data within the index and a no cluster index storing only reference to the data within the index is known as covering indexes or index with included columns, which stores some of the table columns within the index. This allows some queries to be answered by using the index alone, in which case the index is said to cover the query. As with any kind of duplication of data, cluster, any covering index can speed up reads, but they require additional storage and can add overhead on writes. Databases also need to go to additional effort to enforce transaction guarantee because applications should not see consistency due to the duplication. Multi-column indexes, the index discussed so far only map a single key to a value. That is not sufficient if we need to query multiple columns of a table or multiple fields in a document simultaneously. The most common type of multi-column index is called a concatenated index, which simply combines several fields into one key by appending one column to another. The index definition specifies in which order the fields are concatenated. This is like an old-fashioned paper phone book, which provides an index from last name, first name to phone number. Due to the sort order, the index can be used to find all the people with a particular last name, or all the people with a particular last name, first name combination. However, the index is useless if you want to find all the people with a particular first name. Multidimensional indexes are a more general way of querying several columns at once, which is particularly important for geospatial data. For example, a restaurant search website may have a database containing the latitude and longitude of each restaurant. When a user is looking at the restaurant on a map, the website needs to search for all the restaurants within the rectangular map area that the user is currently viewing. This requires a two-dimensional range query like the following. A standard B3 or LSM3 index is not able to answer that kind of query efficiently. It can give you either all the restaurants in a range of latitude at any longitude, all the restaurants in a range of longitude, but anywhere between the north and south poles, but not both simultaneously. One option is to translate a two-dimensional location into a single number using a space filing curve, and then to use a regular B3 index. More commonly, specialized spatial indexes such as R3s are used. For example, PostGIS implements geospatial index as R3 using PostgreSQL, generalized search tree indexing facility. We don't have space to describe R3s in details here, but there is plenty of literature on them. An interesting idea is that multidimensional indexes are not just for geographic locations. For example, on an e-commerce website, you could use a three-dimensional index on a dimensional red, green, blue to search for products in certain ranges of colors, or in database of weather observation, you could have a two-dimensional index on day temperature in order to efficiently search for all observation during the year 2013, where the temperature was between 25 and 30 grades centigrade. With a one-dimension index, you will have to either scan over all the records from 2013 regardless of temperature and then filter them by temperature, or vice versa. A 2D index could narrow down by timestamp and temperature simultaneously. This technique is used by hypertext, full text search, and fuzzy indexes. Full text search and fuzzy indexes. All the indexes discussed so far assume that you have exact data and allow you to query for exact values of a key, or a range of values of a key with a third order. What they don't allow you to do is search for similar keys, such as misspelled words, such fuzzy querying requires different techniques. For example, full-text search engines commonly allow a search for one word to be expanded to include synonyms of the word, to ignore grammatical variation of words, and to search for occurrences of words near each other in the same document, and support various other features that depend on linguistic analytics of the text to cope with typos in documents or queries. Lucene is able to search text for words with a certain edit distance. An edit distance of 1 means that one letter has been added, removed, or replaced. As mentioned in making an LSM3 out of SSL table on page 78, Lucene uses its SSL table-like structure for its term dictionary. This structure requires a small in-memory index that tells queries at which offset in the sorted file they need to look for a key. In level DB, this is an in-memory index. It's a sparse collection of some of the keys. But in Lucene, the in-memory index is a finite state automaton over the characters in the key, similar to a tree. This automaton can be transformed into Levenshtein automaton, which support efficient search for words within a given edit distance. Other fuzzy search techniques go in the direction of documents, classification, and machine learning. See an information retrieval textbook for more details. Keeping everything in memory. The data structure discussed so far in this chapter have all been answered to the limitation of disk. Compared to main memory, disks are hard to deal with. With both magnetic disk and SSD disk, data on disks need to be laid out carefully if you want good performance on reads and writes. However, we tolerate these awareness because these have two significant advantages. They are durable, their content are not lost in the power is turned off, and they have a lower cost per gigabyte than RAM. As RAM becomes cheaper, the cost per gigabyte argument is eroded. Many datasets are simply not that big, so it's quite feasible to keep them entirely in memory, potentially distributed across several machines. This has led to development in in-memory databases. Some in-memory key value stores, such as memcache, are intended for caching use only, where it's acceptable table for data to be lost if a machine is restarted. For others, in-memory databases designed for durability, which can be achieved with special hardware such as battery power RAM. By writing a lot of chain to disk, by writing periodic snapshots to disk, or by replicating the in-memory state to the other machines. When an in-memory database is restarted, it needs to reload its state either from disk or over from network from replica unless special hardware is used. Despite writing to disk, it's still an in-memory database because the disk is merely used as an append-only log for durability, and reads are served entirely from memory. Writing to disk also has operational advantages. Files on disk can easily be backed up, inspected, and analyzed by external utilities. Products such as VaultDB, MemSQL, and Oracle Timestamp are in-memory databases with a relational model, and the vendors claim that they can offer big performance improvement by removing all the overhead associated with managing on this data structure. RAM Cloud is an open source in-memory key value storage with durability, using a log structure approach for the data in memory as well as the data on disk. Redis and on Couchbase provide weak durability by writing to disks asynchronously. Counterintuitively, the performance advantage of in-memory databases is not due to the fact that they don't need to read from disk. Even a disk-based storage engine may never need to read from disk if you have enough memory, because the operating system cache recently used disk block in memories anyway. Rather, they can be faster because they can avoid the overhead of encoding in-memory data structures in a form that can be written to disk. Besides performance, another interest area of in-memory databases is providing data models that are difficult to implement with disk-based indexes. For example, Redis offers a database-like interface to various data structures, such as priority, queues, and sets. Because it keeps all data in memory, its implementation is comparatively simple. Recent research indicates that an in-memory database's architecture could be extended to support datasets larger than the available memory, without bringing back the overhead of a disk-centric architecture. The so-called anti-caching approach works by evicting the least recently used data from memory to disk when there is not enough memory, and loading it back into memory when it's accessed again in the future. This is similar to what operating systems do with virtual memory and swap files, but the databases can manage memory more efficiently than operating systems, and it can work at the granularity of individual records rather than entire memory pages. This approach still requires index to fit entire memory, though, like the big cast example at the beginning of the chapter. Further changes to storage engine design will probably be needed if non-volatile memory (NVM) technologies become more widely adopted. At present, this is a new area of research, but it's worth keeping an eye on the future. Transaction processing or analytics. In the early days of business data processing, a write to the database typically corresponds to a commercial transaction taking place, making a sale, placing an order with a supplier, paying an employee salary. As databases expand into areas that didn't involve money changing hands, the term transaction nevertheless stuck, referring to a group of reads and write that forms a logical unit. A transaction need necessarily have ACID, atomicity, consistency, isolation, and durability properties. Transaction processing just means allowing clients to make low latency read and writes, as opposed to batch processing jobs, which only run periodically, for example, once per day. We discussed the ACID property in chapter 7 and batch processing in chapter 10. Even though databases started being used for many different kind of data, comments on blog posts, action in a game, content in address book, the basic access pattern remains similar to processing business transactions. An application typically looks up a small number of records by some key. Using an index, records are inserted or updated based on the user input. Because these applications are interactive, the access pattern becomes known as online transaction processing, OLTP. However, databases also started being increasingly used for data analytics, which has very different access patterns. Usually, an analytics query needs to scan over a huge number of records, only reading a few counts per record, and calculate aggregate statistics such as count, sum, and average, rather than returning the raw data to the user. For example, if your data is a table of sales transactions, the analytic query might be: what was the total revenue of each of our stores in January? How many more bananas than usual did we sell during our latest promotion? Which brand of baby food is most often purchased, together with brand X diapers? These queries are often written by business analysts and fed into reports that help the management of a company make better decisions. Business intelligence, in order to differentiate this pattern of using databases from transaction processing, has been called online analytic processing (OLAP). The difference between OLTP and OLAP is not always clear cut, but some typical characteristics are listed in Table 3.1. Comparing Table 3.1, comparing characteristics of transaction processing versus analytic system. Property, main read pattern. OLTP, small number of records per query fetched by key. OLAP, aggregated over large number of records. Main reading pattern, random access, low latency write from user input, bulk input ETL or event stream. Primarily used by end user customer via web application, internal analytics for decision support. What data represent latest state of data, current point in time, history of event that happened over time. Dataset size, gigabytes to terabytes, terabytes to petabytes. At first, the same database were used for both transaction processing and analytic queries. SQL turned out to be quite flexible in this regard. It worked well for OLTP type queries as well as all AP type queries. Nevertheless, in late 1980s and early 1990s, there was a trend for companies to stop using the OLTP system for analytics purpose and to run the analytics of a separate database instead. This separate database was called a data warehouse. Data warehousing. An enterprise may have dozens of different transaction processing systems, system powering the custom-facing website, controlling point of sales, checkout system in physical store, tracking inventory in in warehouses, planning routes for vehicles, managing suppliers, administering employees, etc. Each of these systems is complex and needs a team of people to maintain it, so the system end up operating mostly autonomous for each other. These OLTP systems are usually expected to be highly available and to process transactions with low latency, since they are often critical to the operation of the business. Database administration therefore closely guard the OLTP databases. They are usually reluctant to let business analysts run ad hoc analytic queries on an OLTP database, since those queries are often expensive, scanning large part of the dataset, which can hurt the performance of concurrently executing transactions. A data warehouse, by contrast, is a separate database that analysts can query to their heart content without affecting OLTP operations. The data warehouse contains a read-only copy of the data in all the various OLTP systems in the company. Data is extracted from OLTP databases using either periodic data dump or a continuous stream of data, transforming into an analyst-friendly schema, clean it up, and then load it into a data warehouse. This process of getting data into the warehouse is known as extract, transform, and load, and is illustrated in Figure 3a. Data warehouses now exist in almost all large enterprises, but in small companies they are almost unheard of. This is probably because most small companies don't have so many different OLTP systems, and most small companies have a small amount of data, small enough that it can be queried in a conventional SQL database, or even analyzed in a spreadsheet. In a large company, a lot of heavy lifting is required to do something that is simple in a small company. A big advantage of using a separate data warehouse rather than querying OLTP system directly for analytics is that the data warehouse can be optimized for analytic access pattern. It turned out that the indexing algorithm discussed in the first half of this chapter works well for OLTP, but are not very good at answering analytical queries. In the rest of this chapter, we will look at storage engines that are optimized for analytical instead. The difference between OLTP databases and data warehouses. The data model of the data warehouse is most commonly relational because SQL is generally a good fit for analytic queries. There are many graphical data analysis tools that generate SQL queries, visualize the result, and allow analytics to explore the data through operations such as drill down, slicing, and dicing. On the surface, a data warehouse and a relational OLTP database look similar because they both have a SQL query interface. However, the internal of the systems can look quite different because they are optimized for a very different query pattern. Many databases vendors now focus on supporting either transaction processing or analytic overload, but not both. Some databases, such as Microsoft SQL Server and SAP HANA, have support for transaction processing and data warehousing in the same product. However, they are increasingly becoming two separate storage and query engines which happen to access through a common SQL interface. Data warehouse vendors such as Teradata, Vertica, SAP HANA, and Paracel typically sell their system under expensive commercial licenses. Amazon Redshift is a hosted version of Parcel. More recently, a plethora of open source SQL on Hadoop projects have emerged. They are shown but aiming to compete with commercial data warehouse systems. These include Apache Hive, Spark SQL, Cloudera, Impala, Facebook Presto, Apache Tahoe, and Apache Drill. Some of them are based on ideas from Google's Dremel. Stars and snowflakes, schema for analytics. As explored in Chapter 2, a wide range of different data models are used in the realm of transaction processing. Depending on the needs of the application, on the other hand, in the analytics there is much less diversity of data models. Many data warehouses are used in a fairly formulaic style, known as star schema, also known as dimensional modeling. The example schema in Figure 3.9 shows a data warehouse that might be found at the grocery retail. At the center of the schema is a call fact table. In this example, is a call fact sales. Each row on the of the fact table represent an event that occurred in a particular time. Here, each row represents a customer purchase of a product. If we were analyzing website traffic rather than retail sales, each row might be represent a page view or a click by user. Usually, facts are captured as individual events because this allows maximum flexibility of analysis later. However, this means that the fact table can become extremely large. A big enterprise like Apple, Walmart, or eBay may have tens of petabytes of transaction history in its data warehouse, most of which is in fact tables. Some of the columns in the fact tables are attributes such as price at which the product was sold and the cost of buying it from the supplier, allowing the profit margin to be calculated. Other columns in the fact table are foreign key reference to other tables, called dimension tables. Each row in the fact table represents an event, the dimension represents who, what, where, when, how, and why of the event. For example, in figure 3.9, one of the dimensions is the product that was sold. Each row in the dim product table represents one type of product that is for sale, including its stock keeping unit, SKU. Description, branding, category, fan content, package size, etc. Each row in the fact sales tables uses a foreign key to indicate which product was sold in that particular transaction. For simplicity, if the customer buys several different products at once, they are represented as a separate row in the fact table. Even date and time are often represented using dimensional tables because these allow additional information about dates, such as public holidays to be encoded, allowing queries to differentiate between sales on holidays and non-holidays. The name star schema comes from the fact that when the table relationships are visualized, the fact table is in the middle surrounded by its dimension table. The connection to these tables are like the rays of a star. A variation of this template is known as the snowflake schema, where dimensions are further broken down into subdimensions. For example, there could be separate tables for brand and product categories, and each row in the dim product table could reference the brand of the category as foreign key, rather than storing them as a string in the dim product table. Snowflake schemas are more normalized than star schema, but star schema are often preferred because they are also simple for analytics to work with. In a typical data warehouse, tables are often very wide. Fact tables often have over 100 columns, sometimes several hundred. Dimension tables can also be very wide, as they include all the metadata that may be relevant for analysis. For example, the dim store table may include details of which services are offered at each store, whether it has an in-store bakery, the square footage, the date when the storage was first opened, when it was last remodeled, or how far it's from a nearest highway, etc. Column-oriented storage. If you have trillions of rows and petabytes of data in your fact table, storing and querying them efficiently become a challenging problem. Dimensions tables are usually much smaller, millions of rows. So in this section, we will concentrate primarily in storage of facts. Although fact tables are often over 100 columns wide, a typical data warehouse query only accesses 4 or 5 of them at one time. Select dot queries are rarely needed for analytics. Take the query in example 3.1. It accesses a large number of rows. Every occurrence of some buying fruit or candy during a 2013 calendar year, but it's only need to access 3 columns of the fact sales tables: the key, product SK, and quantity. The query ignores all other columns. How can we execute this query efficiently? In most OLTP databases, storage is laid out in a row-oriented fashion. All the values from one row of a table are stored next to each other. Document databases are similar. An entire document is typically stored as a continuous sequence of bytes, but you can see this in a CSV file example. And in order to process a query like, you may You may have indexes on fact sales, data key, and fact sales product SK. That tells the storage engine where to find all the sales for a particular data for a particular product. But then a row-oriented storage engine still needs to load all those rows, each consisting of over 100 attributes. From these into memory, parse them and filter out those that don't meet the required conditions that can take a long time. The idea behind column-oriented storage is simple. Don't store all the values from one row together, but store all the values from each column together instead. If each column is stored in a separate file, a query only needs to read and parse those columns that are used in that query, which can save a lot of work. This principle is illustrated in figure 310. Column storage is easy to understand in a relational data model, but it's applied equally to non-relational data. For example, Parquet is a columnar storage format that supports a document data model based on Google's demo. The column-oriented storage layout relies on each column file containing the rows in the same order. Thus, if you need to reassemble an entire row, you can take the 23rd entry from each of the individual column files and put them together to form the 23rd rows of the table. Column compression. Besides only loading those columns from disks that are required for a query, we can further reduce the demand of the disk throughput by compressing data. Fortunately, column-oriented storage often lends itself very well to compression. Take a look at the sequence of the value for each column in figure 310. Then, often looks quite repetitive, which is a good sign for compression. Depending on the data in the column, different compression techniques can be used. One technique that is particularly effective in data warehousing is bitmap encoding, illustrated in figure 311. Load the bitmaps for product SK equal 31 and store SK equal 3. And calculate the bitwise AND. This works where the column contains the row in the same order. So the k bit in one column bitmap corresponds to the same row as the k bit in another column bitmap. There is also various other compression schemes for different kind of data, but we won't go into them in detail. See 50A reference for an overview. Column-oriented storage and column families, Cassandra and HBase, have a concept of column families, which they inherit from Bigtable. However, it is very misleading to call them column-oriented, which within each column family, they store all columns from a row together, along with a row key, and they do not use column compression. Thus, the Bigtable model is still mostly row-oriented. Memory bandwidth and vectorizing process. For data warehouse query that needs to scan over million rows, a big bottleneck is that bandwidth for getting data from this into memory. However, that is not the only bottleneck developers of analytical databases also worry about efficiently using the bandwidth for main memory into CPU cache, avoiding branch misprediction and bubbles in the CPU instruction process pipeline, and making use of single instruction multi-data SIMD instruction in modern CPUs. Besides reducing the volume of data that needs to be loaded from disk, column-oriented storage layouts are also good for making efficient user CPU cycles. For example, the query engine can take a chunk of compressed column data that fits comfortably in the CPU L1 cache and iterate through its tile loop. That is, with no function call. A CPU can execute such a loop much faster than code that requires a lot of function calls and condition for each record that is processed. Column compression allows more rows from a column to fit in the same amount of L1 cache. Operators such as bitwise and AND, all described previously, can be designed to operate on such chunk of compressed column data directly. This technique is known as vectorized processing. Sort ordering in column storage. In a column storage, it doesn't necessarily matter in which order the rows are stored. It's easier to store them in order in which they were inserted, since the insertion of a new row just means appending to each of the column files. However, we can choose to impose an order, like we did with SSL tables previously, and use that as an index mechanism. Note that it wouldn't make sense to sort each column independently because we will no longer know which item is in the column belong to the same row. We can only reconstruct a row because we know that the kth item in one column belongs to the same row of the kth item in the another column. Rather, the data needs to be sorted an entire row at a time, even though it is stored by columns. The administrator of the database can choose the column by which the table should be sorted using the knowledge of common queries. For example, if query of the target date ranges, such as the last month, it might make sense to make date key the first sort key. Then the query optimizer can scan only the rows from the last month, which will be much faster than scanning all rows. A second column can determine the sort order of any row that have the same value in the first column. For example, if they key is the first sort key in figure 310, it makes sense for product SK to be the second sort key so that all sales for the same product on the same day are grouped together in storage. That will help queries that need to group a future sale by product within a certain data range. Another advantage of sorted order is that it can help with compression of columns. If the primarily sort column does not have many distinct values, then after sorting, it will have long sequences where the same value is repeated many times in a row. A simple row-leg encoding, like we used for the bitmap on figure 3.9, could compress that column down to a few kilobytes, even if the table has billions of rows. That compression effect is stronger on the first sort key. The second and third sort key will be more jumbled up and does not have such a long runs repeatedly value. Columns further down, the sorting priority appears in the section random order, so they probably won't compress as well. But having the first few columns sorted is still a win overall. Several different sort orders. A clever extension of this idea was introduced in C store and adopted in the commercial data warehouse vertical. Different queries benefit from different sort of orders, so why not store the same data sorted in several different ways? Data needs to be replicated to multiple machines anyway, so that you don't lose data if one machine fails. You might as well store that redundant data sorted in different ways so that when you are processing a query, you can use the version that best fit the query pattern. Having multiple sort orders in a column-oriented store is a bit similar to having multiple secondary indexes in a row-oriented store. But the big difference is that the row-oriented store keeps every row in one place, in the heap file or a cluster index. And secondary indexes just contain pointers to the matching row. In a column store, they normally are not any pointer to data elsewhere, only columns containing values. Writing to column-oriented storage. This optimization makes sense in data warehouse because most of the load consists of large read-only queries run by analysts. Column-oriented storage, compression, and sorting all help to make those read queries faster. However, they have the downside of making writes more difficult. An updating place approach like B-tree use is not possible with compressed columns. If you want to insert a row in a video of the sorted table, you will most likely have to rewrite all the column files as row identified by the position with the column the section has to update all columns consistently. Fortunately, we have already seen a good solution early in this chapter. LSM3 all writes first go to an in-memory store, where they are added to a store structure and prepared for writing to disk. It doesn't matter whether the memory store is row-oriented or column-oriented. When enough writes have accumulated, they are merged with the column files on disk and read into a new file in bulk. This is essentially what Vertical does. Queries needs to examine both of the column data on disk and the recent writes in memory and combine the two. However, the query optimizer hides the distinction from the user. From an analyst's point of view, data has been modified with inserts, updates, or deletes is immediately reflected in subsequent queries. Aggregation, data cubes, and materialized views. Not every data warehouse is necessarily a column store. Traditional row-oriented database and a few other architectures are also used. However, columnar storage can be significantly faster for ad hoc analytical queries, so it's rapidly gaining popularity. Another aspect of data warehouse that is worth mentioning briefly is materialized aggregates. As discussed earlier, data warehouse queries often involve an aggregate function, such as count, sum, average, min, max in SQL. If the same aggregates are used by many different queries, it can be wasteful to crunch through the raw data every time. Why not cache some of those count or sum that query use most often? One way of creating such a cache is a materialized view. In a relational data model is often defined like a standard virtual view, a table-like object whose contents are the result of some query. The difference is that a materialized view is an actual copy of the query result written to disk, where a virtual view is just a shortcut for writing queries. When you read from a virtual view, the SQL engine expands it into the view underlying query on the fly and then process the expanded query. When the underlying data change, a materialized view needs to be updated because it is the normalized copy of the data. The database can do that automatically, but such updates make write more expensive, which is why materialized views are not often used in all TP databases. In read-heavy data warehouse, they can make more sense whether or not they actually improve read performance depending on the individual case. A common special case of materialized view is known as data cube or OLAP cube. It is a grid of aggregates grouped by different dimensions. Show an example. Imagine for now that each fact has foreign key to only two-dimensional tables. In figure 312, these are date and product. You can now draw a two-dimensional table which dates along one axis and products along the other. Each cell contains the aggregate sample sum of attributes, net price for example, of all facts with the date product combination. Then you can apply the same aggregate along each row or column and get a summary that has been reduced by one dimension, the sales by product regardless of date, or the sale by day regardless of product. In general, facts often have more than two dimensions. In figure 3.9, there are 5 dimensions: day, product, store, promotion, and customer. It's a lot harder to imagine what a 5-dimensional hypercube would look like, but the principle remains the same. Each cell contains the sales for a particular day, product, store, promotion, customer combination. This value can be repeatedly visualized along each of the dimensions. The advantage of a materialized data cube is that certain queries become very fast because they have effectively been pre-computed. For example, if you want to know the total sales per store yesterday, you just need to look at the total along appropriate dimension. No need to scan millions of rows. The disadvantage is that a data cube doesn't have the same flexibility as query the raw data. For example, there is no way of calculating which promotion or sale comes from the items that cost more than 100 because the price is one dimension. Most data warehouses therefore try to keep as much raw data as possible and use aggregates such as data cubes only as a performance boost for certain queries. Summary. In this chapter, we try to get the bottom of how databases handle storage and retrieval. What happens when you store data in databases, and what does the database do when you query for the data again later? On a high level, we saw the storage engine fall into two broad categories: those optimized for transaction processing and those optimized for analytics. There are big differences between the access pattern in those use cases. OLTP systems are typically user-facing, which means that they may see a huge volume of requests in order to handle the load. Applications usually only touch a small number of records in each query. The application requests record using some kind of key, and the storage engine uses an index to find the data for the request key. Disk seek time is often the bottleneck here. Data warehouse and similar analytic systems are less well known because they are primarily used by business analytics, not by end users. They handle a much lower volume of query than OLTP systems, but each query is typically very demanding and requires many millions of records to be scanned in a short period of time. This bandwidth, not seek time, is often the bottleneck here. And column-oriented storage is an increasingly popular solution for this kind of workload. On the OLTP side, we saw a storage engine from two main schools of thought. The log structure school, which only permits append to a file and deleting obsolete file, but never update a file that has been written. Bitcast, SSL table, LSML table, level DB, Cassandra, HBase, Lucene, and others belong to this group. The update in place school, which treats the disk as a set of fixed sizes pages that can be auto-reading. B-trees are the biggest example of this philosophy, being used in all major relational databases and also many non-relational ones. Block structure storage engines are a comparatively recent development. Their key idea is that they systematically turn random access write into sequential write on a disk, which enable higher write throughput due to the performance characteristics of a hard drive and SSDs. Finish of the OLTP side, we did a brief tour through some more complicated indexing structure and databases that are optimized for keeping all data in memory. We then took a detour from the internal of a storage engine to look at the high-level architecture of a typical data warehouse. This background illustrated why analytical workloads are so different for OLTP. When your query requires sequential scanning across a large number of rows, indexes are much less relevant. Instead, it's become important to encode data very compactly to minimize the amount of data that the query needs to read from this. We discussed how column-oriented storage help achieve this goal. As an application developer, if you are armed with this knowledge about the internal of the storage engine, you are in a much better position to know which tool is best suited for your particular application. If you need to adjust the database tuning parameters, this understanding allows you to imagine what effect a higher or lower value may have. Although this chapter could make you an expert in tuning any of one particular storage engine, it has hopefully equipped you with enough vocabulary and ideas that you can make sense of the documentation for the database of your choice.